In section 12.6, we're going to look at how to solve exponential and logarithmic equations. So here's again a page from the book, which is the homework exercises from section 12.6. The highlighted ones are the ones that you're doing for your homework, and I will be doing the ones very similar to these, and of course probably more than what you see in highlights. Now, any homework problem that has this calculator icon next to it right here, that means you should use calculators in order to find the value or an approximation to the answer. So for my purposes, I'm not going to really be interested in these types of exercises. We're going to look at the ones where we don't need calculators. And if you look at later on, there's a good chunk of them right in here that require calculators. So we'll actually take a look at the ones that are like the exercises you're doing. Okay, so let's actually start by going through these two principles. That's all we have in this section. One of them we've already seen before, the top one, the principle of exponential inequalities. And for this one, because of the one-to-one property of exponential functions, we can say that if 2x in an equation, this is an exponential equation. In an exponential equation, when bases are common, the exponents must be equal, is equivalent to that expression. And a similar principle exists for logarithmic equalities that, given these conditions, are met, of course. X equal y is equivalent to log base a of x equals log base a of y. So in other words, let's say if I have a logarithmic equation now, where I have a single log on the left and a single log on the right side, it's almost like canceling the logs. Then x and y, we can set them equal to each other. Okay. And let's take a look at some exercises now. That's all we have in here. Now, for starters, we're going to look at page 825. Exercise number 10 is the one that we're going to start this section with. Exercise number 10. So in exercise number 10, here the equation is 2 to 3x equals 64. 2 to 3x equals, sorry, I'm not sure why this is acting funny. There you go. 2 to 3x equals 64. Okay. And so this is an exponential equation because the variable is in the exponent, right? The variable, which is x, appears in the exponent and makes this exponential equation. Now, to start with, this is what we're going to do. I'm going to rewrite 64 in base 2, right? 2 to the 6th power is going to be 64. So here we're looking at the first type of exponential equations where we have same bases. You see the base is 2 here and it is the same base here. These are actually pretty easy to solve because directly from the principle of exponential equality we can say that bases are common, exponents must be equal. And from this, we divide both sides by 3, and x is 2, and we are done. It was really that simple. So if the exponential equation has expressions that have the same base on either side, then we do them this way. Now, for exponential equations, by the way, because the domain of exponential functions are all real numbers, means x can be anything. I don't usually check the answer if I'm comfortable with the process on how I got the answer. It'll be good to verify the answer, but it's not necessarily, which is not the case for logarithmic equations. For those, I'll explain. We have to check our answers. But for exponential equations, we need not do that. Let's take a look at exercise number 16 now. In exercise number 16, now the equation is 2 to the x minus 1 is equal to 8. And again, the right side, I can get it as a base 2. So again, here's a case where we have a common base. So that means x minus 1 should equal 3. So they look identical, the right and the left side. And from this, add 1 to both sides, and x is 4. And we've solved this one. Okay. And let's see. Let's take a look at number 20. Now, in number 20, again, we have an exponential equation, e to t equals 20. Now, here is a case where we do not have the same base. Okay, so we don't have a common base in this one. So, how are we going to work this? The easiest way to solve these kinds of exponential equations is to translate them or rewrite them in logarithmic form. Okay, so I'm just going to say write in logarithmic form. And remember how that went. The log form, let me remind you how that went. So if we have x equals a to the y, this means log base a of x is y. So this is what we mean. If you look at the left side, that's an exponential equation. The right side is a logarithmic equation. So we're going to rewrite this, translate it, rewrite it in log form. And in log form, it's going to look like this. It's going to become, remember, the base will be the base. The base in exponent will be the base in the log. 20 goes in front of g, and t goes on the other side. And usually, again, the way I check is that e to the power of t should always look like that when you write it in logarithmic form. So this is the rewrite of just the expression. And if you note, we actually solved for t. See, t is isolated. So from this, t equals. Now remember, a log base e is a natural log, true? So I'm just going to write ln of 20, and that is the answer to this one. Pretty slick, huh? All we have to do is just rewrite it in logarithmic form, and that solves it. Now, of course, you're welcome to use a calculator if you want to approximate it, but for me, that's good enough. We're done with that one. Okay. So here again was a case where the exponential equation had different bases on either side. Let's take a look at number 26. In exercise number 26, we are given 29 is equal to 3e to 2x. So first I'm going to isolate the exponential function by itself. So that means e to 2x is equal to, divide both sides by 3. And I swapped out the position. What's on the left, move to the right. What's on the right, I move to the left. So nevertheless, I divided both sides by 3. Now, this is just like number 20. So I'm going to rewrite this one now in logarithmic form. So this becomes in logarithmic form. So here's log. Base will be e. And then 29 thirds goes in front of g equals 2x. And there you have this one. And again, as a way of check, e to 2x looks like what the equation looks like on the left, right? E to 2x, e to 2x, that's what this is. And at this point, that means just a natural log, right? Log base e. So I'm going to write 2x equals ln of 29 thirds. And the final step to isolate x, divide by 2. So x is equal to you can write it as 1/2. Multiply both sides by half. It's the same thing. ln of 29/3. Now, this is good enough. Most people leave them like that, but I actually can go another step further. Remember this property of logarithms, or the rule of logarithms. We said log base a of m to p is equal to p log base a of m. Remember that property? Well, p is the exponent, right? That moves in front of a log. So I can see 1/2 just like the way p is in my property to the right. So there you go. I'm looking at 1/2 here, and I'm looking at p here. So I can actually move p as an exponent on the argument m here. So in other words, I'm going to move 1/2 as an argument, as an exponent on 29/3. The argument is 29/3. So this is going to make it equal to ln of 29/3 to 1/2. And another property we have is, if anytime we have a to 1/2, we can write that as a square root of a, can't we? We did that in chapter 10. So all said and done, this is natural log of a square root of 29/3. Again, this is probably overkill. But anyway, that's the exact answer to this exponential equation. Again, I didn't assign this or anything like this one, but I thought, some of you may be interested in how these are done. So we're good with number 26, everyone, I hope. And let's move on to number 30 now. Okay, so in exercise number 30 now. Number 30, we're beginning to work logarithmic equations now. So for this one, I have log base 2 of x equals 6. Now, this is a logarithmic equation where we have just one log on the left side. So the easy way of doing these is to translate them in exponential form. In exponential form, remember, we write this as 2 to the 6th equal x, and there, the equation solves itself. The answer is 2 to the 6th, that's 64. Now, for logarithmic equations, this is very important, because the domain of logarithms, let me real quick just throw in a log in here. There you go. Some kind of a log, whatever that log is, doesn't matter. It's just some log function. Okay, our focus is on domain. Here's x values. If you recall, the domain has to be positive, right? X must be positive, otherwise the function is undefined. And this one is log base a of x. Okay, I'm assuming base a is greater than 1 because of the shape of the log. But again, that's not the point. The point is that the domain has to be positive, which means the implication is we must, it is not an option, we have to check the solutions to logarithmic equations. So this number 64, I have to plug it in. Now here's how I verify it. You plug in a 64 in for x, and if it makes the argument positive, we're good. And in this case it does. So this becomes log of 64, and 64 is in the domain. It's a positive number, so the answer is good. Now sometimes we plug in a positive answer into the argument, depending on the expression in the argument, and the argument becomes actually negative once, let's say, it adds, subtracts something from it. So remember, don't just look at the answer. If it's positive, that's the answer, and if it's negative, you reject it. What I said was that the argument of a log, when you plug it in, the answer, the proposed solution, when you plug it into the argument of a log, the argument must be positive. The answer to x could be positive or negative. As long as it works in the argument, we're good. So we'll see example of cases where this won't happen and we have no solution. But for now, we are good. The answer to this is 64. Let's take a look at number 44 now. In exercise number 44, we have 3 natural log of x is equal to negative 3. So for this one, again, I'm going to divide both sides by 3, and ln of x equals negative 1. Now, because there is a single log, just like number 30, I need to translate it in exponential form. Well, in order to translate in exponential form, I'm going to go ahead and put that base e on there. Remember, natural logs are log base e. This is actually going to help me see the next step. The next step is to write in exponential form, right? So this is going to become e to the first power is equal to x, and the equation is solved. So x is equal to e. Remember, e is about 3, right? 2.71 and change. So when I plug it actually back in, when I plug in this e back into here, the argument is going to be positive. So that is a good solution in number 44. And oops, sorry, this was negative 1, right? I know some of you probably said, hey, you forgot the negative there. That's e to negative 1. And let me just erase that part. So the answer is e to negative 1, which, by the way, you can write it as 1 over e. Usually they don't like negative exponents, so there you have it. The answer is 1 over e. In number 49, we have log that has no base. So it's just log of x minus log of x plus 3, and that is equal to 1. Now remember, if the base is not written, what is it? 10, correct? That's what that is. So I'm going to actually go ahead and put those on there because we're going to need that in a minute. Now, because I have 2 logs on the left, we need to consolidate. We need to combine them into log of a single expression. And I'm going to use the properties of logarithms to do that. If you remember, we had this property of logarithms, the quotient rule. Log m over n is log m minus log n. And of course, this works in any base, right? Any valid base, a. So, because it is in the form of a subtraction, right in here. So this is the first part. This part is log m. This part is log n. So I can actually write it as a quotient, and that's what I'm going to do next. I'm going to write this as log of a quotient, which would be x on top, x plus 3 on the bottom, and the base is of course 10. Remember, in the book they did not put the base because it's a common log. So next I'm going to rewrite it in exponential form. And in exponential form, x divided by x plus 3 should equal to 10 to the first power, which is just 10. Now I have a fraction equal a number. Let's multiply both sides by x plus 3, or we can cross multiply them. There, if you give it a denominator of 1 and cross multiply. If you cross multiply, you're going to cross multiply x by 1 and x plus 3 by 10. Okay, so this becomes 10 times x plus 3 equals x. Distribute 10x plus 30 equals x. And then we're going to solve for x. Not too bad. We can subtract x from both sides and subtract 30 from both sides. And from this we get x is negative 30 over 9. Okay, now we need to check the solution. So hopefully again you followed the steps here. So my first step, just to recap, I combine these into one quotient. And then the second step, I rewrote it, that equation, in exponential form. And once we did, then I multiply both sides, say by x plus 3, or cross them. You cross them this way. This is what I got. Now, the answer, remember, we always have to check the answer. True? So I'm going to check the answer, and here's how you check it. Take this answer, right in here, and plug it in. If the argument is negative, it's no good. Not because the answer is negative. I'll give you an example where the answer will be negative and it's a good answer. But not in this case, because when you plug in the negative number, it actually makes the argument negative. Okay? Now, let's see. And there's no need to check the other one, by the way. Once it fails one of them, you don't need to check the other. And it's also very important. You always check the answer in the original equation. If you do it in here, it's going to work. You can try it. If you plug negative 30 over 9 in here and work the fraction, it will work. But don't put it into this step. Put it in the original equation. So, because the answer is not going to work, we're going to say there is no solution in this one. No solution. In other words, the only potential solution is the one that did not work. And again, I want to emphasize we need to check the solutions to all logarithmic equations. Now, this was exercise number 49. Let's take a look at exercise number 52. Okay, in exercise number 52. This one goes log of x plus 1 and negative log x equals 0. So again, I'm going to write it as the ratio of logs, x plus 1 over, not ratio of logs, but log of a ratio. There's a difference. Basis 10 equals 0. Now, rewrite in exponential form, and this becomes x plus 1 over x equals 10 to 0, which is 1, right? Any non-zero to 0 power is 1. Next, we can multiply both sides by x, right? And the x's cross out, right? The x here and the 1 in the denominator cross out. This becomes x plus 1 equals x. Now, if I subtract x from both sides, minus x here, then these will add to 0. We get 1 equals 0, which is of course not true. This is false. True? So that's just a sign that there is no solution in this one. I'm just going to write no solution. And there we go. Number 52 is solved. Okay. Now, let's take a look at, we're going to look at 3 more exercises and we'll be done with this section. Again, the more we do, it's, I guess, the better, because you can watch these videos at a later time. We're not so tired and you actually get more from it. Okay, let's take a look at number 56. In exercise number 56, here we have an equation that has several logs in it. X plus 3 plus log of x plus 2 equal log on the other side. So again, here's the example of having there are logs on each side of the equation. So one thing we could not do, you cannot drop the logs. You cannot cancel logs. Okay, we can't do that. So the right way of doing it is to actually combine the 2 logs on the left as a log of a single expression. I'm going to use the multiplication rule for that. And here's the right side. Excuse me. Next step, now we can use the one-to-one property of logarithms. Remember the principle of logarithmic equality? Now we can think of as if you're actually dropping the logs now. Okay, so we can write it as x plus 3 times x plus 2 equals 20. For two logs to be equal, they have the same base. They have to have the same argument, right, in order to be equal. Now here, one thing you got to be careful, something I cannot do. Let me put cannot. I cannot say x plus 3 is 20 or x plus 2 is equal 20. Okay. The zero factored property only works when there's 0 on the right side. Again, this may be tempting because this factored form, nice factored form, equal 20, but this won't work. In other words, if two things, remember these are factors, if two numbers multiply to 20, one of them need not be 20 necessarily, right? It could be, but it doesn't have to be. For example, this could be a 4, that could be a 5. So x plus 3 need not be 20, x plus 2 need not be 20. That's what this says here. So be careful again, only with 0 on the right side, that would make sense. So what do I need to do? I need to actually FOIL these out, right? So I'm going to go x squared plus 2x plus 3x plus 6 equals 20. Combine like terms, right, and then subtract 20 from both sides. And now we got our quadratic equation. And this quadratic equation actually turns out to be factorable. Okay, so the factored form is going to be x minus 2x plus 7 equals 0. Remember how the factored form works. We need two numbers that multiply to negative 14, and the same two numbers add to 5. The two are negative 2 and 7. The product negative 14, and they add to 5. Okay, so we can write x minus 2 is 0, or x plus 7 is 0. X must be 2, and here x must be negative 7. Okay. Now, remember, this is a logarithmic equation, so that means I have to check the solutions. True? Let's plug in a 2. If I plug in a 2 in here, I get 2 plus 3, 5. That's good because the argument is positive. Now, we have to check it also in here, not just the first one. In there, I get 2. 2 plus 2 makes 4. That's also positive. So this is a good answer. We'll take that answer. Now the other proposed solution, potential I call them, until we check them, is negative 7. So if I plug in a negative 7 now, okay, if I plug in a negative 7, let me now remove this one and remove that one. And let's actually try negative 7 now. So when I plug in negative 7 into this logarithmic expression, negative 7 plus 3 is negative 4. See, that's less than 0, isn't it? So this isn't going to work. We're going to throw that one out. And there's no need to check the other one, the second one, right? There's no need to check this one. Because if it fails this, doesn't matter whether it works in here or not, which by the way it doesn't. Negative 7 plus 2 fails this also. All it takes is one of them. So we're going to rule out negative 7, and the final solution to this is x equals 2. This equation has only one solution. Okay, that was number 56. Now let's take a look at number 60. In number 60, actually, this one is a natural log, one that has natural log. Number 60. Number 60, the expression is ln of x minus 6, and then plus ln of x plus 3 equals ln of 22. Okay, so again, notice you have multiple logarithmic expressions in here. Do not cancel the logs. It will be incorrect. So on the left side, we're going to put the logs together. X minus 6, x plus 3 equals ln of 22. And when you have a single log on the left, a single log on the right side, see a single log on the left and a single log to the right, that's the only time you can cancel them. Okay, which is now. So about now, we're going to cancel them. So, and then I'm going to FOIL these, so you get x squared plus 3x negative 6x minus 18 equals 22, with the logs disappeared or logs gone. That makes x squared negative 3x. Actually, let's subtract 22 from both sides, so I get negative 40 equals 0. And then this time again we're looking for two numbers that multiply to negative 40, add to negative 3, and the two numbers are 5 and negative 8, right? Plus 5 minus 8, the product negative 40, the sum negative 3. Let me move to the other up here. Now over here, I'm gonna set x plus, I don't need parentheses, so I'm just gonna let x plus 5 be 0 and separately x minus 8 0. So I get what I call potential solutions at this step. So I have two potential solutions here. One of them is x negative 5. The other one is x equals 8. Now let's check them and see if they work. And here's negative 5 goes in and it makes this expression negative 5 minus 6 negative 11. So we're going to cross this one out. We're not going to use this one. Let's try 8 in there. When we plug in the 8 in here, 8 minus 6 is 2. That's good. We still have to check it in here also. Okay. So now 8 plus 3, 11. That's good also. And we can actually say that's the answer. Now just to show you a full-blown check, okay, one that actually shows x equals 8 is the solution. Let me show you how the check works. Again, the way I did it just a moment ago suffices for what we're doing, but if you actually want to see how do I plug in and show the left equal right, that's what I want to do. 8 minus 6 plus ln of 8 plus 3, will it equal to ln of 22? Let's see if it does. So 8 minus 6, that's 2, plus 8 plus 3 is 11. Will that equal to ln of 22? Doesn't look like it the way it is, huh? But remember, using properties of logarithms, I can write the left as 2 times 11. And that is equal to ln of 22 because you have 22 on the left, 22 on the right. And it checks. And again, you don't need to do this the way I've been doing it. It works well. Just plug in the number. As long as the argument is positive, we're good. And there you go. That's exercise number 60 now. And let's take a look at number 66. I believe number 66 is the last one from this section. So exercise number 66. And number 66 goes like this. You have log base 4 of x plus 6 negative log base 4 of x equals 2. Okay, so first we got to put the logs together. Don't cancel or don't try to rewrite it in exponential form because we can't. So that's going to be, because of the subtraction here, this is going to be ratio of x plus 6 divided by x, and that whole log is equal to 2. And now I can actually write it in exponential form. So in exponential form, x plus 6 over x is equal to 4 squared, which is 16. And let's multiply both sides times x. So this way I can cross the x there and the x in the bottom. And it becomes x plus 6 equal to 16x, right? That's 16 times x. Let's subtract x from both sides. And this becomes 6 equals 15x. And finally, if I divide both sides by 6, divide by 15, because we want to isolate x. Divide by 15, and I get 6/15, which reduces down to 2/5, right? Divided 3 from the top, 3 from the bottom. So the potential solution is x is 2/5. Again, it's potential until we check it and make sure it works. Now, plug 2/5. I'm plugging in 2/5, okay, in here. 2/5 plus 6, that's 6 2/5, which is positive, so that's good. And of course, plug it into here. That's 2/5, again, positive, that's good. So yes, this is a good solution, and right in here, we're going to buy that as solution to that exercise. So with that, we are done with this section. Again, I hope you followed everything we did. And if not, please review and just review everything we've done, and hopefully you'll be able to follow what we've done here. Okay, and we're done with this section.